So like we said, the standard deviation, this will encompass certain percentages of your data. So that's where these two theorems come in. We're going to start using standard deviation. We're going to use it a little bit. Then we're going to take a break and we're going to do probability, chapters 3 and 4. And then we'll go back to using standard deviation a lot. Okay, so this first one, you have two theorems here. You have this first one here is called Chebyshev theorem. And I never spell it right. I think it is spelled right on there. So Chebyshev's theorem is going to work for any distribution. So uniform, normal, skewed, whatever. So if it says in the question that the distribution is skewed, that's when you're using this typically, because otherwise you're going to want to use the one down here. So in a skewed distribution, we use this, but we can use it for any. So the definition is this: at least 1 minus 1 over k squared % of data fall within k standard deviations of the mean. What does that mean? Okay, how much % of data falls within 2 standard deviations of the mean? So if I make k 2, that's 1 minus 1 over 2 squared. Well, 2 squared is 4. So that's 1 minus 1/4, which is 75%. So 75% of data will fall within 2 standard deviations of the mean. And then 3 standard deviations, I would do the same thing. It would be 1 minus 1 over 3 squared, which would be 1 minus 1/9, ends up being about 89%. And we usually don't go more than 3 standard deviations. And all right here. Okay, all those numbers are here for you. So there's the Chebyshev right there. Then there's the empirical rule. So the empirical rule works for normal distribution, which most distributions we're going to use are normal distributions, or symmetrical. And then this is, we call this the 68, 95, 99.7 rule, because you're going to start using it a lot and memorize it. 68% of data is going to fall within 1 standard deviation of the mean, 95% within 2 standard deviations of the mean, and 99.7 within 3 standard deviations of the mean. So within 3 standard deviations of a mean, you should encompass almost all of your data. All right, so let's do some examples here with this. So example 8.1, the scores on a recent statistics test were skewed left with a mean of 75 and a standard deviation of 10. Determine at least what percentage of students scored between a 55 and a 95. I have a drawn out curve here because sometimes it helps to visualize it, but you don't have to draw it out. This is a normal curve. So that's not the right curve for this because it's skewed left. So you can kind of like redraw this. Skewed left is going to look more like this, where more of the data is over here, or sorry, more of the data is over on the other side, the right. You know, because it's a test, so there's going to be more scores above 50 than there are below. Hopefully, hopefully, right? Okay. So because it's skewed, though, we're going to use Chebyshev. Chebyshev. Okay, because of the skew. Because you can't use the empirical rule unless it's normal. So I want to show you guys how this sets up here. So you have these points. This is just a number line with 1, 2, and 3 standard deviations marked on here. So the middle would be right here. This is the middle of the number line. We'll make that your X bar. That's your 75. So you would put 75 here. And then it says a standard deviation of 10. So, okay, the average score was 75, give or take 10 points. So what that looks like is this. 10 points to the left would be 65. And then to the right or above would be 85. And then another 10 points would be 55 and 95. And another 10 points would be 45 and 105. So really what's happening there is we're looking at this mean. You have X bar, and then this is plus 1 standard deviation, 2, 3 standard deviations. And this is minus 1, 2, and 3 standard deviations. Okay, so back to the question. Let's see, what percentage of students scored between a 55 and a 95? If I look at that, here's 55, here's 95. That's 2 standard deviations. 55 and 95 are 2 standard deviations. According to Chebyshev's theorem, what percentage of students, or sorry, what percentage is 2 standard deviations of the mean? 75%. So that's your answer there. So you can put that out and look, or you could, do it mathematically. I like to look at it as a graph when I look at it. But 2 standard deviations, 75%. That's all you have to do there. Now, you might have another question that said, okay, well, if 200 students took the test, how many scored in this range? Then you would just do 75% of 200. Let's do another example. Okay, if the data in example 1 were known to be normally distributed, then what percentage scores between 55 and 95? It's still 2 standard deviations. So, but it's normally distributed. So because it's normally distributed, we use the empirical rule. So for the empirical rule, what percentage is 2 standard deviations? 95. And then just to show you, this is a normal curve. And then what that looks like is, it would be the same numbers. It's just symmetrical now. So you would still have 75, then 65 and 85, then 55 and 95, and 45 and 105. And then there's your 2 standard deviations. Now the thing about this curve, we're going to be exploring this a lot when we get chapter 6 and 7. Underneath this curve covers 100%. So the area under the curve is 100%. So when I say 95% and I color this in, this is 95%, 2 standard deviations. 3 standard deviations, remember, is 99.7. So those tails, or is that 0.3 accounted for on either side? So if I color that in, that's 95%. So let's look at, we got a couple more examples with doing this and some practice problems. I don't know if we'll get to the practice problems. We'll try. All right, so a data set consisting of 500 Wechsler IQ test scores, which is that one that they give, the main one. It's normally distributed. So IQ is actually known to be normally distributed. with a mean of 100 and standard deviation of 15. So this is it's a easy test question. We do IQ and M&Ms, normally distributed. A lot of those. Okay, so you'll see that a lot. Approximately how many scores fall between a Wechsler IQ score of 55 and 145 if there's 500 people that took the test? Okay, so we can draw that out. It's normally distributed, so we're looking at the empirical rule here. So normal, empirical rule. If I draw this out, here's the average score of 100. It has a standard deviation of 15. So minus 15 would be 85, plus 15, 115. Minus another 15, that would be 70. Add another 15, 130. Subtract another 15, 55. Add another 15, 145. So we're looking at 55 and 145, so that's here. So how many standard deviations is this? 3 standard deviations, which according to the empirical rule is 99.7%. So 99.7% of the people that took this IQ test had a score between 55 and 145. So let's see how many that is. So 99.7% of 500, which means we would do 0.997 times 500. So 498.5. You can't have 0.5 of a person, so I'd probably take that and round that up to 499. But it just depends on the question. It might ask you to round or not. This one just says approximately. I'm going to round it to 499. If it marks it wrong, I'll put 498.5. Okay. So pretty much everybody who took the test has that IQ in between there. The more people you test, I mean, think about it. If you had 1 million instead of 500, there's going to be more people that fall outside of that range. 997,000. It's a lot. Okay, so the more data values you have, the more are those supposed, the outliers. They're going to be outside of that 99.7. Okay, last example here. So let's suppose that this was not normally distributed. So that means now we're looking at Chebyshev. Go back here. So not normally distributed, at least 96% of test scores between what 2 scores? Okay, so this one's interesting. I don't actually need the curve for this one. So I have Chebyshev's theorem. So we say this is not normal. So we're going to use Chebyshev. And I think we only went to 89% when we were doing that. But we can look at this by just using the formula and reverse engineering it, right? So we have the formula is 1 minus 1 over k squared as a percent would give us the percentage. We want to find k now. So 96%, if we add that in here, we can do the formula. We can find k, right? So we would take this 1 minus 1 over k squared equals 96. Subtract 1 from both sides. Gives us negative 1 over k squared equals 95. Move that k squared out of the denominator. Those cancel. I get negative 1 equals 95 times k squared. Divide by 95. Those cancel. So I get negative 1 over 95 equals k squared. And I want k, so I'm going to take the square root. So let's see what that is. So -1 divided by 95, square root of that. This is a negative number. What did I do here? Oh, oops. My bad. I need the eraser. Oh, why is this so small? It's 0.96, not 96. So I gotta fix it from right there. We don't want 95. Okay, 0.96. That makes a big difference, right? 0.96 minus 1 is 0.04, negative 0.04. Not 95. So then you have -1 equals negative 0.04k squared. Then if you divide both sides by negative 0.04, the negatives are going to cancel. So I don't have to do a negative underneath the square root. So I get +1 over 0.04. Let's do that one. So 1 divided by 0.04, 25. Square root of that, 5. So at least 96% of the scores would then lie between those two scores in the 5. So just don't forget the decimal if you have a question like that. So you have some practice problems here, and I'm just looking here. Yeah, I'm going to let you guys work on this. I think I have a video of them done, but if not, I'll just do a video just going over the practice problems for you.